I'm going to go over some of the general slides about the background of the tutorial and motivation, and then Chase will actually do the tutorial. So I assume if you are here, you probably are at least motivated by some text applications, or you are curious about what this is all about. But we all know that text data are everywhere. As I'm speaking, if they are recording this speech, this will become text. And some others are probably writing tweets. So we generate a lot of text data, and it's about all kinds of topics. Now, interesting way to look at the applications of text data is to think about the text data as the data that are generated by human sensors. And this is, in some sense, very similar to a thermometer or objective sensor, like a network sensor that would sense the world and then report a number. For example, the thermometer would say, well, the temperature is some number at this point in this room. But similarly, a human could also sense the temperature and then say, well, I feel cold or feel hot here. But humans are much more intelligent than a physical sensor. And we are also subjective. So those are two key differences. And that would make text data both challenging for data mining and also uniquely useful for applications. So because we're subjective, what we report is not necessarily the truth. So for example, Chase might say, I feel cold, but I feel warm here, and even though we are in the same room, right? And that creates some challenges in recovering the truth. So, spams in social media or reviews would cause problems for data mining. But on the other hand, that provides great opportunities for us to understand people, because the data that we reported has traces about ourselves, how we think about things, our attitude, our mood. You can imagine building a forecasting application by mining tweets to forecast people's mood about some issues. Right, so both of the challenges and opportunities. But this also means text data has to play an important role in all big data applications. Why? Because we always have people involved in all domains, be it health or security, whatever. Right? We have people there, and people will generate the text data. And for any text data, for any big data application, we should combine all kinds of data, not just non-text data, but also text data. So for that reason, it's going to play a role in all the big data applications. And you can think about your own applications and to see if there are text data that are relevant. Right? Secondly, it's especially useful for understanding people, and that's also very important in all applications. In order to optimize the collaboration of intelligent systems and people, you need to understand people. And then finally, because it directly encodes knowledge after intelligent processing of the world, and it's very important to understand some of the direct statements about knowledge. Now, the general techniques used to build these text data applications can be roughly classified into two groups. They're not strictly, hard separations of these techniques. One is called text retrieval, and one is called text analysis or text mining. Now, text retrieval consists of techniques that are used for turning a large set of text documents, for example, the whole web, into a much, much smaller set of highly relevant documents for a particular problem. In any particular problem, we are only interested in that small subset. It's important to reduce the amount of data to that subset of relevant data, both for the sake of efficiency and also for the sake of removing noise. And then text analysis roughly refers to techniques that we can further apply to turn the found relevant documents into actionable knowledge that you can actually use for decision making or for any applications. But of course, text retrieval also is useful for providing knowledge provenance after data mining. But roughly, these are the two kinds of techniques. I highlighted some specific techniques in each category. Again, they are not clear separations. So for example, on the text retrieval side, you see search engine applications. Pretty much wherever you have text data, you have a search engine. So web and also vertical domains, but also on your laptop or pretty much anywhere you have text data, you have faced the problem of search. And recommender systems or email filtering or summarization, those are all techniques to help people get connected with the right data. Typically, it's an interactive process. But after that, we do data mining, do deeper analysis of text data, And that would involve the use of techniques like clustering, categorization, or topic analysis, topic of discovery, trend analysis, sentiment analysis, or using text data for prediction of pretty much anything, even stocks. Right? So I also listed a lot of application domains here, from medical health to security to education to business, etc. Now, this tutorial is about a unified toolkit called Meta that can support the development of such applications, and that covers text retrieval and text analysis in a unified manner. I think one of the unique characteristics of the toolkit is that it can actually integrate the search and analysis, including also machine learning and natural language processing algorithms together in a unified toolkit, which is very important for a really sophisticated application that involves both steps. Right, so without further ado, well, I actually should mention that after this tutorial, you should, hopefully, you should all be able to build some of these applications by using Meta. But we also hope you can work together with us to extend Meta, which is open source tool, to make it even more useful for many applications. So without further ado, I'm going to turn the stage to Chase, who is going to actually do the tutorial.
Juggling lots of different technology at the same time. Okay, so hi again. I'm Chase Geigle. I am one of the main developers behind the Meta Toolkit effort. The other main contributor being Sean Massung, who's actually the founder of the project. This was done under the advice of Cheng. And as Cheng was mentioning, right, one of the main goals for Meta is to provide sort of a one-stop shop for doing your text analysis for whatever project that you have in mind. And so in order to do that, we have to support a wide range of different kinds of tasks. So this tutorial, I'm going to slowly start to walk you towards the end goal of building applications. We'll have to start at the very, very basic level, like I have strings that are in text documents, now what? All the way to, okay, now that I've done some semantic parsing of the documents, how do I use that in order to predict what the native language of a particular author was? So we'll do some fun stuff today. The toolkit itself is it's all open source. It's MIT and NCSA licensed, which means that if you're here from industry, as I suspect many of you are free to go ahead and use that, modify it, sell it, do whatever you want. It's an open source permissive license, so no GPL here, which is a deliberate choice. The actual toolkit itself is written in C++. It's actually written in C++ 11 and 14, but the tutorial, we're going to be using the Python bindings for it. So this provides a sort of a nice higher level abstraction to be able to interact with these highly efficient learning algorithms that are implemented in C++ for speed reasons. So sort of depending on what end of the spectrum you sit on, you might be using the Python bindings to use the tools that are built into Meta. And if you're planning on extending it, you'll be writing things in efficient C++ after you've prototyped in Python. So we're gonna spend most of today in the Python world, but do know that there is a very, very efficient C++ library underneath everything. Pretty much all of my research work has been added to the toolkit over time. So and that same story is true for Sean. So this is constantly being updated. If you look at the release time for the version of the Python bindings we're going to be using today, you'll see that they're very, very recent, as in a couple hours. So I'm a little bit tired, but it is being actively developed. That's my point. And as far as deployment, our biggest sort of customer, but not really customer, would be the MOOC courses. So Cheng has taught a couple different Coursera MOOCs where they use Meta as part of the assignments and projects. So it's been used by many thousands of students at this point. And I'm going to attempt to, we're going to try and break things up. I don't know where it must be a little bit later. But I'm going to try and break things up so we have the coffee break at the same time as other people are having the coffee break. But then when we come back, we're going to be doing a mini like 30-minute Kaggle for a couple different kinds of applications. So when it says hands-on, I really truly mean hands-on. So if you have your laptop, get it out. If you do not have Python installed, please install Python. And hopefully you'll be able to follow along. Okay. So, right, this is kind of if there's a table that motivates meta, this is it. Because as text mining researchers, right, our pain point was if we wanted to do something that sort of spanned these two different major pillars of text mining applications, the retrieval and the analysis, we had to turn to a bunch of different toolkits, right? If we needed to be able to, well, I don't want to run topic modeling on my entire corpus, I have too much text, but I want to run topic modeling on some subset of my corpus, and I want to select that according to some query. Well, now I need a search engine. I also need something to do the topic modeling. And before I do any of that, I need something to do the feature extraction, because I need to figure out what my document representation is going to be for the topic modeling. Am I going to do n-grams, bigrams, et cetera? And so you quickly discover that if you're going to do anything remotely interesting in the domain of text, that you're going to be pulling in like 4 or 5 different tools. And that is kind of a hindrance to doing sort of exploratory analysis of text data. So Meta's goal is to try and get as many things as possible in one place so that you can not immediately have to reach for another tool if you want to do something slightly different. And this was all discussed in an ACL demo paper. Okay, so before the break, this is kind of the pipeline for all of the things that are part of Meta. You start with a corpus of text. That corpus is then consumed by this feature generation pipeline, which is what we're going to spend most of our time on before the break, because feature engineering and generation for text is actually probably the most important thing, because if you don't have representation, you don't have any application. So we're going to spend a sizable amount of time talking about doing feature representation and feature engineering for text. And then once we have these features, we analyze these features to come up with document representations, and then these document representations are put into indexers, either an inverted index or a forward index, depending on which view of the data is most appropriate for the task at hand. Search is going to use an inverted index. Most other things are going to be using a forward index, or you might be using both, because you need both views. Once you have the indexes, then you go and build all the different applications that use these on-disk data structures. So before the break, we'll talk about the feature engineering and indexing, and after the break, we'll do the actual applications. So it's where we'll have the mini Kaggle. So please come back and enjoy competing amongst each other for a short competition. I don't have prizes, unfortunately, but I think it'll be fun. Okay, so this is kind of the rough outline. We'll see how I'm not bad. I'm a little over, but it's okay. So we're gonna sort of try and break things up this way. So after the break, we'll do the major applications. I'll try and leave a little bit of time at the end for any feedback that you have, and just sort of to summarize what we talked about. Okay, so we're gonna write code today. We're gonna write a lot of code today. So to get started, I have all of the code and stuff for the tutorial is available on our website. If you go to meta-toolkit.org, or if you just Google Meta Toolkit, it'll be the first result. And then on the left side, actually I can show you. I don't know why I'm. So if you go to the website over here, there's the KDD 2017 MetaPy tutorial, and the entire IPython notebook that I'll be walking through today is available here. So if at any point I'm going too fast, please let me know. If at any point you tuned out and responded to an email and then don't know where you are anymore, use this to catch back up, because everything I'm doing is sort of incrementally building upon the previous examples, so we kind of need to be building that shared state. But it's all here, so please feel free to look at that. If there's a longer code snippet or a URL, it may be handy to copy and paste that from here, so just keep this particular resource in mind. I am going to be using Jupyter Notebook to do this, so if you're not familiar, it's a nice integrated Python environment. you can, if you have Python and the Python package manager pip installed, you should be able to get started with everything by doing something like this. First, make sure your pip is up to date so that you can get the binary wheels that Meta is using. It is great. And then we should be able to grab, hopefully, my internet. Okay, there we go. If you pip install, upgrade Jupyter and MetaPy, you should have the Python environment that I'm using and also the actual Python bindings themselves. Then you can get started with Jupyter Notebook. That'll run in the terminal, and somewhere else in your browser, it'll open up the actual Jupyter Notebook page. So that's on this page for me. And we're going to start with a new Python 3 notebook. I'm using Python 3. Meta supports pretty much all variants of Python that are reasonably in existence at this point, so anything from 2.7 on. So whatever flavor of Python you happen to be using, it should be fine. I'm preferring to use 3 because that's what's default on my system, but use whatever you've got. Yeah. So I'm going to just cancel them so that you can see the 3 commands. So the first thing is just make sure that your Python package manager is up to date. And Jupyter is the particular, you don't have, this step is optional. You can just use a regular Python shell if you want, but I prefer using Jupyter just because it's nicer. So you can grab that, and then pip install upgrade MetaPy, and it should give you version, I think, 0.25 right now. Yeah?
Is this also installing the C++ binding or just the Python bindings?
So the Python bindings are written basically by binding the C++ to the Python C interpreter underbelly. So this is downloading a binary compiled version of the C++ with the Python bindings attached to it.
So you don't pull that on with Brew or anything?
No, yeah, it's just you should be able to, if your pip is up to date on OS 10, Windows, or Linux, you should be able to just be off to the races. It does require a 64-bit operating system, but if you're dealing with anything of reasonable size or anything made in the last like 5 years, you should be fine. Yeah.
So relatively new to Python, so
Sure.
vice versa, so this might be silly, but is your control C at the end actually part of
No, I'm just trying to silence the output so you can actually see all 3 commands. Yeah. Sorry, what now? Yeah. I won't be using the actual C++ code today, but if you go to metatoolkit.org, we have a GitHub for the actual. They're both the MetaPy and Meta are sort of developed as 2 sort of separate projects, one that depends on the other. So you can absolutely go and grab the C++ version and start from there. There's no requirement to use Python. I'm just using it here because it's a little bit easier to get started.
So you have a developer's package and a user's package?
That's one way of thinking about it, yeah. We found that using the Python bindings for like writing assignments and stuff for students has been an easier experience than thrusting C++ 14 at them when that's C++ is getting less commonly covered, so there's some advantages. There's advantages using it because it's fast, but there's also disadvantages because people haven't had experience with it. So I'm trying to strike a nice balance by offering both sort of perspectives on the tool. Okay, does everybody have MetaPy installed at this point? Do you have a question, or is that just a confirmation? I'm going to treat that as a confirmation. Okay. Great. So where did there? Nope. There it is. All right. So if you have Jupyter opened, you should be able to just make a new notebook, and we'll do everything through here. I'm going to try and follow the notebook on the website as closely as possible, but I may add or remove things as time permits. So the very first thing is to make sure we actually import MetaPy. Just as a quick sanity check, everybody should be on 0.2.5. If not, run the command, the pip install -- upgrade metapy to make sure you upgrade the version. I don't think that should have happened unless anybody checked this out like earlier before the tutorial happened. But just as a sanity check, we'll make sure everybody's on the same version. I am going to set it up to generate log output on standard error so that we can see progress while it's indexing or any other sort of slow operations. You can choose to do that or not, depending on what your setup is. And now let's actually start doing the very beginning of feature representation. So everything starts with a document, and conceptually a document is just a big long string, right? It came from somewhere. Where it came from doesn't really matter in this case. Maybe it came from a separate file. You have one file per document, or maybe it's a line in a corpus where each line is a document. But you end up with a document that's just a series of characters. So we'll start there with, let's make our document. This makes a blank document, so in the index submodule of metapy, there's document. We'll set its content, so whatever your favorite sentence is, it doesn't really matter. I'm just coming up with something here. And now that we have the document as a string, we need to be able to start to pull features out of it. And the most common approach, and one of the most effective, apart from a lot of these newer deep neural network models, the most common and effective standard baseline that you should always try first is going to be the bag of words representation. So we're going to start building towards the bag of words representation. First thing we have to do there is be able to look at this text and figure out where are the words. So this part is called tokenization. And the tokenizers in Meta sort of kick off the feature analysis pipeline. So you can think of the pipeline as being, we start with a tokenizer, which produces a stream that we can then iterate through of all the different words in the sentence. For each token that we observe, we might want to apply some transformations to it. We might want to normalize things to all be lowercase. We might want to remove numbers. We might want to drop words that we know are just function words that don't add anything to the meaning of the text, that are just there because it needs to be there to be grammatically correct. We might want to do any number of these sort of transformations on the tokens that are coming out. So you can think of, you start with the tokenizer, and then sort of each filter sort of plugs into the output of the previous one. You end up with a filter chain that at the very end of the filter chain gives you the actual tokens you want to consider. So these are probably lowercase, maybe normalized to be no longer than a certain length to get rid of noise and other garbage in the data, etc. Then once we have that finalized token stream, we then consume the entire stream to generate the document representation. So let's start with a tokenizer. The sort of standard tokenizer that we use all the time is the ICU tokenizer. And the reason for that is tokenizing actually is sort of surprisingly difficult. You might think, well, just split on spaces, right? And that might be fine if your data is really clean. But if your data came from any real source, it probably has things like characters from other languages. It might have Unicode combining characters. It may have things that don't fit in the ASCII code page. If you live in wonderful, clean ASCII land, yeah, you can just split on spaces and it's great. And there's a built-in there's a tokenizer, white space tokenizer, that does exactly that. But if you're dealing with web documents, you all of a sudden now you have to actually care about Unicode. And so the ICU tokenizer is actually using the standard Unicode library. It used to be IBM's library, but it's actually its own organization now. It's as part of the Unicode standard. And so if you use the ICU tokenizer, it's breaking the text into pieces according to rules set forth by the actual standard for this is how Unicode works, and these are where word boundaries are supposed to be as a unified thing across all applications. So that's why that's the default, because most of the time you're dealing with documents that came from the internet, and we have to care about these things. All right, so the tokenizers and filters all live in the analyzer submodule, so we can grab an ICU tokenizer by creating one like that. And now let's see, what this does. So we can set the content of the tokenizer to be the content of our document. So that just sets up the initial, okay, that's what I'm operating on. Now the tokenizer is ready to start spitting tokens at you. And let's just iterate through the token, or we'll build a list of the tokens just to see what they look like. So the tokenizer basically gives you an iterable, so you can do whatever generator expressions and stuff you want with that, or do a regular for loop. This is just a way of generating a list of all the tokens in the document. And I had a typo, which will happen. Okay. So this split sort of predictably on the white space. Oh, and it consumed, I think it consumed the initial token. There we go, okay, yeah. I was wondering, I was like, wait, something's missing, okay. Because I typoed. Okay, the other thing you might notice here is that there's sort of these like pseudo XML looking things at the beginning and ending. These are sentence boundary markers. So one of the side effects of using the ICU tokenizer is that it actually will also identify where the breaks between sentences are, which is useful if you're going to do sort of analysis on a broader window than a single word. If you start considering which words are adjacent to each other, knowing that this word ended a sentence is now very important. So we have these sentence boundary tags to be able to tell you where the beginning and ending of sentences are, so you can construct multiple windowed features that also include the boundaries. If you're only looking at words, the sentence boundary tags are meaningless, so we can just tell the ICU tokenizer to not output them. Yeah? So in theory, yes. In practice, I haven't tried. So the ICU standard provides some model for doing Chinese and Japanese word segmentation. I think they also have models for Arabic. I don't know what their quality is. So I would try it, and then only if you have evidence to suggest that it's not working well enough, then throw another model at it. We have sequence tagging components as part of the library, so it'd be very easy to go ahead and train a CRF, for example, to do Chinese word segmentation, and then build your own tokenizer that uses the output of your CRF to do something like that. I don't have a pre-trained model, I guess is what I'm saying. But I think ICU will do a halfway decent job, and then I would only care about that if you actually are observing that it's not doing a good enough job for your application. Yeah?
I have a question. Do you have a tokenizer to handle emails and URLs? I was just trying it out, and then it seems to break up URL and email into like the
Yeah.
information.
Yeah, so in most of the applications I've been dealing with, URLs end up being essentially noise for me. Because I'm not searching for documents that have this particular URL or something in it. So I don't have one that is specifically focused on that. Yeah, you would want to be able to detect which things are or aren't URLs, and then sort of sidestep that part of the tokenization for that sort of thing. It shouldn't be too bad to build a modified ICU tokenizer. If you had like just a regular expression, you should be able to detect this looks like a URL, so just don't break it apart, and then start from there. Okay. Right. Okay. So so if we go back, I'm going to grab my document. I'm going to add another sentence to show that it actually is doing multiple sentences. Update my document's content, and then reset the tokenizer to be doing operating over the content of the new document, and you can see it's identified the boundary portions between the sentences. So this is useful for things where I want to break down my document not at the word level but on the sentence level. If, for example, I need to do some sort of NLP to identify the part of speech tags in a sentence, I need to figure out where the sentences are first, right? So ICU tokenizer is good for that. It's a good default. It's not going to be perfect all the time, and that's why there's the different tokenizers that are available, and you can also write your own because it's figuring out what your initial word units are is quite important. Yeah. It's based on a number of things. So the ICU tokenizer is based on the actual Unicode standard. So there's a chapter in the Unicode standard that says for any Unicode string, this is how you figure out where word boundaries are. And that's useful for, in applications being able to do something like that where you double click and it figures out where the word boundaries are. That's using ICU to do that, basically. So the tokenizer is using that algorithm to figure out where the word boundaries are. So it's for English, it's mostly looking for white space characters, right? But they have models for languages that don't have white space characters that should be able to provide words as well.
So I just tried the Chinese characters, and I think it works.
Okay.
I can show you the result, but you have to be careful. When you do when you specify the string, you need to use kind of English format of the quotation marks. It seems like that's
yeah, there's when you create. I just haven't played with a lot of things that are not in sort of the Romance language family. There's a way you can specify to the ICU tokenizer which locale that you're expecting the documents to be in. So if you're dealing with a primarily Chinese corpus, I think there's a setting that probably will change what it expects quotations and stuff to be, and then it will probably do a little bit better on that.
Question.
Yeah.
Do you have a sentence splitter that can be trained on different corpus?
So we have sequence labeling algorithms, so you could absolutely do that. I don't have a pre-trained one, but you could absolutely train your own if you can. You just have to convert it to be a sequence labeling problem, and then you can throw our CRF or our structured perceptron at it and go there. All right. Good. Very active audience. I like this. Okay. So. Right. So for now, we're just going to do unigrams for now, just because we're starting at the very basic, and we'll build up from there. So I'm going to instruct. I'm going to go and I really want this to be. There we go. I'm going to go build a tokenizer again, but I'm going to tell it I'm only going to do unigrams, so I don't care. Don't bother analyzing where the sentence boundaries are, because I don't want a feature that is the feature begin of sentence happened. I don't care. So we can just tell it to suppress tags. And now if we do, oops. Now if we do that, sentence boundary tags are magically gone. All right, so let's start from here. We could just throw this directly into an application at this point. We do have words, but it's often really useful to do. Sorry, yeah.
Just scroll a tiny bit so we can see.
Sorry. Thank you. Do call me out on stuff like that. If I'm covering up things that you want to read. Right. So we could start here, and we could just throw these into our downstream task. And it may work, but the problem here is that there's going to be a lot of features that are being generated at the very end that may or may not be particularly useful. Like I may not care about the difference between capitalized and lowercase forms of the same word, right? I probably want to collapse those down to the same word. I may also not care about things, or maybe I really care about things that are above a certain length, because it's probably just some a parsing error in extracting the text of the HTML, and you end up with some, garbled mess that it did something terrible to a table, and it's not going to give you any meaningful words. So let's start to build up a filter chain just to see what it looks like. Let's start with a length filter. So this is going to select tokens that fall into a certain length range. So I can tell it, ignore everything that's, shorter than, 2 characters in length, and ignore everything that's bigger than like 30 in order to sort of condense the tokens that I'm considering. Oh, I went out of order. That's okay. So I can do that to sort of get rid of a lot of the punctuation marks and that sort of thing. So and I should mention, because I don't actually remember what the named arguments are, you can do help. And that should tell me, okay, the named arguments are min and max, great. So at any point you can do that. You can call that help function on the submodules to figure out what's available in the analyzers module, or you can call it on an individual class or an individual method of an individual class to see what its signature is. The output could be a little bit better. I'm working on that. But it's at least, it's still useful. It's enough for me to figure out that I need to do length filter. So the filters consume the previous part of the filter chain. So we're going to pass in our old tokenizer. And then we're going to say, let's only consider things that are at least 2 characters, and just throw anything that's a single character. And then let's get rid of anything that's longer than 30. And now we should be able to do and see that it's gotten rid of some of the punctuation marks, I, things that probably aren't going to be all that useful. Okay, in the same domain of just flat out removing tokens, a common goal in a lot of the information retrieval tasks is to remove stop words. Stop words are words that sort of show up in almost every sentence, or at least at the level of a document in every single document. And if you have a feature that's present all the time, it's often not very helpful for helping you do filtering, which is one of the major things that you're doing in a search application, right? So I'm going to grab a stop word list, a standard stop word list that we have from the toolkit website here. I'm gonna use wget. If you're on Windows, you're gonna have to use a browser or figure out how to use PowerShell to download a file. I don't Windows, so I have no idea. This is a point where actually I'm just gonna do that. This is a point where it's useful to actually copy and paste things from the website. Don't need these. Yeah. So I'm just going to grab one in particular, but you could use your own stop word list. Oh no. Everybody's hitting the internet. Okay, that's fine. So I have it loaded here. Okay, that eventually loaded. So now I have the ability to copy and paste things from here. Okay. So where is the URL? This is the URL I'm looking for. So if you just go to that page, you hit Control-F, stopwords.txt, you should be able to find the URL pretty easily. Yeah, are you on Windows?
Yeah.
Yeah, so just go to the URL and just and copy the file over. You can probably use like the requests library for Python to actually download the file or something.
If you're using a Windows system, you can just go to that URL and download the file and then save it. Then you can unzip it and uncompress it. and then you need to copy the directory that's needed for this.
So the stop words list isn't compressed, but they'll be compressed things later. So you'll need to have like 7-zip or something later on.
Just put it in the directory where you have your Python installed.
Okay, so now I've got the stop word list. So let's add a stop word remover to our filter chain. So the way we do this is with a list filter. List filter can operate in 2 different modes. It can either be set in accept mode or reject mode. In reject mode, it says anything that's on the list that you've given me, if I see that token, I will just suppress it. If it's in accept mode, it says, is the token that I'm looking at in my list? If it's there, I will show it to you, and if it's not, I'll remove it. So you can use this to say, this is what I want my vocabulary specifically to be, and you can use that to limit your vocabulary for any downstream tasks that you have there. But the more common approach is, I have a blacklist. I don't want any of these words, these specific ones I just don't care about. So you can use that to say, okay, just get rid of any of these additional words. So that's how we're going to use it. So first argument to all the filters is the tokenizer. I'm going to give it the path to the list, which in this case is Lemur stop words, because this is the stop word list we lifted from the Lemur toolkit. Now I need to give it a mode, so starting to scroll a little bit here, but this is the tokenizer is the meta-analyzer's list filter. First argument is always the previous tokenizer, then the file. Now I'm giving it the reject type, and you can import as and save typing space if you want, but I prefer to be verbose. I'm not sure why. Oh, and I think that's it. Okay, so now we've removed quite a bit. These were sort of dummy, simple example sentences which happen to have a lot of stop words, right? So we've removed quite a bit of extraneous features here. Yeah?
Do you have to give the list filter a file? Can you just give it a list of words?
Right now, you have to give it a file. Patch is welcome. You should be able to give it. There's no reason you shouldn't be able to give it an array. But
In case of a window, is there any way to assign the location to the file? To some kind of path?
here?
Yeah.
Path to the file.
Just put the directory.
Can you?
Yeah, you can put it. Yeah, you can say like or something. Or because I'm on something that doesn't have drive names, it would be like that.
Other noise words, it seems like that case sensitive. It's probably should be case sensitive to filter itself.
Yeah. So let's alter our filter chain, right? So to make sure that we don't fall into that issue, let's make sure that we lowercase first before applying the filter. Right? That way, if your filter list is all lowercase words and you lowercase everything beforehand, it should make sure to match that. That's a great observation, right? These are exactly the sort of things that you need to be thinking about when you're constructing your filter chain, because the order matters, right? Because each thing is consuming the output of the other. So if you want to make sure that you're definitely getting rid of all the stop words, you should probably lowercase first. So let's do that. I'm going to start. I'm just build the whole filter chain again. We'll start with the tokenizer. Let's lowercase immediately. I'm just going to actually. Oh, I messed up the path now. Example. Okay. Now let's do the list filter. Someone's on Slack. And then what else did I have? List filter. No, I already did list filter. What are the other chains that I was talking about so far? Length filter, yes. Okay. Just grab that. Oh, I didn't remove the sentences. Okay, that's fine. Boom. Boom, boom, boom. Okay, great. Yeah.
You kind of, I don't know, call like glossary sort of expansion. So like if you have acronyms. So for instance, a common example you run into here is IT. Lowercase IT becomes it.
It. Yeah. So I don't, but there are there are filters that modify tokens, and that would be the case where you'd use that. Yeah, that would basically be a substituting filter, right? Where you have like a list of candidate. These are the things I would like to replace, and this is what I'd like to replace them with. So a more
Put a stammer.
yeah, the stemmer. That's what I'm going to go. That's where I'm going now. Yeah. Yes.
What's the question? Is that acronym lookup? Was that the same?
Yeah, he was saying like if you have like IT and you want to make that be information technology, not it. If you lowercase IT, it becomes it, and then it.
Does this support that?
So I don't have a built-in filter to do that, but it would be easy enough to implement, right? As just a you maintain a table of these are the acronyms I want to expand, and when I see that acronym, I output multiple tokens, right? So you're not constrained. The filters are not constrained to have to output one token for each token they see. They can take tokens and split them apart, and that can be useful for so for example, the very first word we have here, can't, right? When you're passing that into like the NLP tools, it's common to normalize that as can and nt, right? Because you can and not, and you separate those out so that it can normalize across the different ways of saying that, the contraction. So in that case, it's consuming the individual token can't and then splits it into two as needed.
That's another question.
Yeah.
Hi, do you have a filter that filters words of a particular part of speech after past tagging?
No, but again, that would be a good application. So we have a filter that transforms the word sequences into part of speech sequences. But it would be straightforward to modify that and say, as now you have the list of tagged words. You just go through and only emit the part of speech the parts of speech you care about. Yeah, not built in, but it'd be easy to add. Yeah.
So, with what I've done in text, I've always run into the problem trying to extract things at a sentence level. It's things like Mr., Mrs., this, that word. I tried that here, and just immediately it didn't seem to work. Is there any way to incorporate that? Problem being, if I try and split at the sentence level, if I have Mr. MR period, in the last name, it'll split that as.
Okay. So there is another tokenizer that you could try that I know deliberately has heuristics for trying to detect exactly that problem. I'm trying to remember what the chain would be. I think the way to do that would be using the white space token. So assuming you're dealing with like English, white space tokenizer to just split on spaces and tabs and that sort of thing, and then I think it's sentence boundary filter or detector, where that one is not using the Unicode standard, but is based on a bunch of heuristics for figuring out where sentence boundaries are, and that might do better on that particular problem. Because I know I've had that same problem before, and I have a heuristic tokenizer for that.
Yeah, I should add that if you work on C++ of this toolkit, then you will be able to actually modify the toolkit, extend it with additional filters that other people can use through this interface of Python.
Yeah. You can define them. You can define them in Python as well. It's just not nearly as fast because global interpreter lock. If you can, my recommendation if you're going to do something like that is prototype in Python. And then once you have something that you like and you want it to be fast, go write in C++. Okay, so sort of coming back, a lot of that initial questions were about how do we transform tokens, not just remove tokens. So one of the things you may want to do with at least many languages is do either stemming or lemmatization. So if you have, for example, runs and running, right? Those two things are really about doing the same thing. So I might want to collapse those both down to the non-inflected form run. So for English, we have an implementation of the Porter 2 stemmer, to do lemmatization for English. For other languages, I don't have lemmatizers yet, but it'd be easy enough to add. If you have a particular model, talk to me and I can go implement it.
I have a question. What
Yes.
about proper nouns?
Proper nouns. So if you wanted to distinguish between the lowercase form and the capital case form for proper nouns, you may not want to do lowercasing in that case, right? So this kind of gets at while there is a sensible default, unigram filter chain for English, it's not always going to be the one you want, right? So which is why I've put in the time and effort into making sure that the filter chain is composable so that you can decide whether you actually want to do lowercasing in this case, right? So if I was gonna, segment out sentences to then go feed like NER, for example, or even when I later do part of speech tagging, I don't lowercase when I do part of speech tagging because, as it turns out, capital letters are really important features. But if I'm doing information retrieval, I probably don't care as much. Because there's trade-offs, right? If you don't lowercase, you explode the number of possible tokens that you consider as being separate things, and that may or may not be what you're doing. So it really depends on what your application is. Okay, sorry. So coming back, let's do some lemmatization. So we're going to use Porter 2. And I think it's filter. So Porter 2 doesn't take any other arguments because there's a particular rule-based algorithm that it uses to do the lemmatization. So now we can go and see that it's shortened. In this case, believe is the only one that it's actually shortened because there's a rule for removing trailing e's. Yeah.
So what is a stemma? Do you have a lematizer?
I don't have a general lematizer for all languages. I just have the one for English. But it would be, yeah, Porter 2 is the one for English. Yeah.
But that is really a stemma, not a lematizer.
Yes, it's a stemmer. Yeah, that's right.
You don't have lematizer built in.
No, not at the moment. But it should. It should slot in pretty easily. Yeah. Yeah. Okay. Yeah.
What is the photo filter doing?
Sorry.
What is the photo filter doing?
Porter 2.
Yeah.
Yeah, so it's this is a stemming algorithm from Martin Porter that tries to normalize different inflected forms of the same word. So if you have like runs, running, ran, it tries to make those all be the same word because intuitively they're talking about the same thing. So removing like plural, making everything singular, getting rid of inflection in terms of tense and that sort of thing. In this case, I don't have but I can build an example here real quick. So.
That is incorrect because it does not include. So a stemma does not understand the morphology of the language. It is.
Yeah, it's just a simple rule-based thing. So it's not yeah.
Yeah, long chart.
Yeah. Based on rules.
Yeah. So it's I just if you want to be technical, yeah, it's not a lematizer, it's a stemmer. But it's the same family of things, right? Fundamentally, what you're trying to do is figure out what the root form of things are, and one way of doing that is to do morphological analysis of the word and figure out what the stems are and stuff, and go from there. Or you can apply a rule-based method. And there are trade-offs.
Yeah, I think we certainly would welcome the community to help contribute more filters that apparently are very useful. But in the interest of time, I noticed that there are only 5 minutes left before the break. Are we breaking at the 9:30?
Yes.
So maybe there are some more interesting stuff that you can
Sure.
show that.
Okay. We're close to being able to. Here. So what I'll do is. I'm just gonna grab a quick sample chain from the site. So let's say this is what we wanted for our sequence of words. Now let's analyze it. We need to get a document representation. So this is where the analyzers come in. So the analyzers will consume a particular tokenizer chain and then iterate over documents and produce representations. So So in this case, we have, sorry, there. Okay, so here we've created an n-gram word analyzer with n is equal to 1, so this is unigram words. And the output of analyzing an entire document is going to be this essentially hash table that maps the word features to their counts. This is an n-gram analyzer, so if we wanted to do bigrams, we can do that. And we would get multiple. We get basically tuples as our keys instead of individual strings.
Is there a limit?
A limit to n?
Yeah.
In the tool, no. In practice, yes, because as you increase n, you have larger and larger feature space to consider. So if you're dealing with n bigger than like 2 or 3, you should really seriously consider doing heavy feature selection to make sure that you're the trigrams or higher that you're extracting are actually meaningful trigrams. But I can set this to something ridiculous, and I get 8 tuples of words. Yes.
Your token object, is there a way to see how many filters have been
Applied to an individual token. So that. Not at the moment. The token. So the token object is actually just a string. So it doesn't keep track of its provenance, I guess is maybe the right word.
So you would recommend just starting, you type out all your filter steps and to do the chain, right?
Yeah. And there's another way we'll see probably after break. We have a configuration format, so you can just do this in a text file rather than writing out the actual filters to construct more complicated pipelines, which becomes nice when you start combining different document representations. Okay, so right, so that's n-grams, and 8 grams, which is sort of ridiculous. So I can also do. So one thing that's sometimes useful for like classification tasks is looking at n-grams of characters. So in that case, you would use a character tokenizer that outputs individual characters. You would follow that with an n-gram word analyzer with n equal whatever your n-gram of characters you want to consider, so maybe 3 or 4, and out would come out instead of individual words as the elements of these tuples, it would be individual characters, and that's just use a character tokenizer instead. Yeah, you say n-gram word analyzer 3 toke, and it would give you trigrams of characters. Okay. Everything else I'm going to need more time to do. I can't show you pause tagging and parsing in 1 minute. So I think we should, if people want coffee, we should break, and then we'll be back at 10 sharp, and I'm going to try and quickly go through the sort of more, so that we'll do more sort of NLP related document representation. So we'll look at part of speech tags. N-grams are part of speech tags, which kind of follow naturally from the n-gram analyzers once you have part of speech tagged sentences. We'll do syntactic parse trees and how to extract features from syntactic parse trees, which can be useful for other tasks like authorship attribution, native language identification, that sort of thing. And then I want to do competition. So when we're back, we're going to do a competition. We're going to do a search competition and a classification competition. So hopefully people are looking forward to that.
I do have a question.
Yeah.
In your paper, in your ACL paper, do you have a detailed description of this particular method or not?
It's not a super long paper, and ACL kind of has big margins, but we do attempt to do it justice. We compare downstream task performance for a number of different applications. So for the search application, the NLP applications, and the machine learning applications, we did a separate comparison against individual tools for those three things.
So we're trying to find those records.
If you go,
I just Google.
yeah, if you do. Now this is probably personalized to me, but it should be one of either the first or the second result. Those are the. Yeah, here we go. So once you're here, this is the citation for it, and the full text is available right here. And then if you want to see like the detailed design, there's an entire API documentation on the website. Yeah.